Okay, so this will be the last recording that I'm going to do before our lecture on Wednesday, where we can actually meet and talk in person and you can ask questions. And what I'm going to bring this back to is then I talked about the center of mass, and it's important because that defines how things, the natural pivot point of some given mass. And that can be a person, that can be a bar, that can be anything. So now let's think about this in terms of forces. So if you think back to first quarter, let's see, what did we say? We said if there's a net force, so force net, what would we have? We'd have this mass times acceleration. And then we say, okay, so if I apply the same amount of force to different sized masses, the more massive something is, the less acceleration I get. The less massive something is, the more acceleration I get. When we talk about rotation, then, we need to think of things in terms of how they move about their pivot point. So let's just remind ourselves that we were defining A in terms of, so my acceleration in terms of, let's see, alpha times a radius. So I can rewrite this, and actually what I'm going to do is go make this little subscript so we know that that's tangential. I'll have then some tangential force. It's going to give me this mass, and now we're going to make the substitution of alpha times r. We're not done yet, because there's something else that we need to do. In order for me to rotate something, I need to, that was a really weird noise, I need to apply a force to some sort of pivot arm. So I need to, if you think about it, if I want to rotate this pen, I need to apply a force where the piece of the force is perpendicular to the axis of rotation. So we can do that by saying, okay, so if I have a force dotted with the radius away from the axis of rotation, and then if I've dotted it with the r on the one side, I'm going to dot it with the r on the other side, and see r dotted with r, they're both vectors, gives me r squared. So I'll have mr squared times alpha. So we have a couple cool things that popped out of here. This here would be defining the inertia. And this here says, how do I have to apply a force to get a rotation? And in fact, the dot product gives me this tangential force times the distance away from the center of rotation times sine theta. So if you remember work, what do we do with work? We said the force applied in the direction of the motion. So if I applied a force at an angle for something moving across the floor, the piece that was parallel to the floor is the piece that made things go. So that was in terms of a cosine. The sine piece says that I don't want parallel. I can push on the center of a circle as much as I want, and I'm not going to make it rotate. The way I'm going to make it rotate is if I get a force going perpendicular to it. So the sine theta pulls out that portion of the force that's tangential to the center of rotation. So I can do this. I can go, so this, I can rewrite this mr squared, come to find out, this would be for a point particle. This mr squared, this inertia here, is for a point particle. And this fr sine theta, or ft dot r, this is torque. So we define torque in terms of inertia and its rotational acceleration. Nice. What we're going to see, and the reason why I left this page up, is I can look at this now and say, okay, I can use this thing that I've done with my center of mass, and instead of, for my center of mass, we divided by the total distance, the total mass. For inertia, we're not doing that, because inertia is looking at how something rotates, how hard or how easy it is to get something to rotate. So if I don't have something straightforward, and this is the only math I'm going to do on this lecture, if I wanted to look then at inertia for, say, that board, what would I do? I do, like, I have my m over L, that still stays, times the integral. Now what am I doing? I'm doing r squared instead. So r squared dr from 0 to whatever. And let's just go for funsies, we'll go from 0 to L. So what I get m over L times, I'm adding 1 to the squared, just integrating, so r cubed, pulling the 3 down, divided by 3, evaluated from 0 to L. Close this off. And I get that my inertia would be, I'm going to have an L cubed, will go in for the R cubed. And so I'll have one of those cancel, so I'll get M times L squared over 3. Give me a second, let me look in your book. If you look on page 300 and 302, you will see this for our thin rod. So we have defined the moment of inertia for a thin rod. Now, having started later in the quarter for this year, we're only going to do a couple more shapes just so you kind of get the feel for how to do this integration and how to define the shapes that you're integrating over for your inertia. But we're going to do all sorts of fun things with torque. So we are going to balance things out and look. That's why I wanted you to do all those free body diagrams and forces and rotation, because now we're going to bring energy into it, and we're going to see about keeping things static. How do I keep things from not moving, because sometimes that's what you want. Or how hard is it to get things to roll, and how the mass needs to be distributed. So for now, before Wednesday, what you can do is look up in the table. It's on page 100. No, not 100. 300. And you'll see a whole bunch of equations that define common shapes. So kind of look at that and try to get an intuitive feel for what makes something's inertia bigger and what makes something smaller. And what I want to remind you of as you're looking through that is just kind of keeping in mind what we said about just a net force. We said the more massive something is, the harder it is to accelerate. And now we've defined this torque being this force making something rotate, so a force applied to a pivot point or to a lever arm, making it rotate. So if I have a big inertia, then I'm going to have a smaller amount of alpha. So take a look at where the inertias are defined for and which ones are smaller and which ones are bigger, and ask yourself if you understand why the difference is between where they're pivoting from. All right, I'll see you on Wednesday.